Hello, today we are looking at the continuous uniform distribution. We have just been looking at continuous random variables. Now remember, continuous, that's definitely an O, random variables. And in our continuous random variables, we had a graph like so, made up of bits and pieces. Then drop down like that. And we said the probability was equal to the area under the graph, which is 1. This is kind of a special case of this scenario. This special case is where it's perfectly uniform, so all the same. And in a continuous uniform distribution, the graph looks something like this. Here we go. So same again, you've got a start and an end, it's flat either side, and in between it is totally uniform, straight. And like in the other graph, the area underneath equals 1. Now, we say here that the graph goes between two values A and B, and that, so the height of our graph, so the area is 1, and of course this mysterious looking graph is just like a rectangle. So, area is base times height, the area is 1, and the base is the difference between here and here, so B minus A, and we don't know the height. The height is our frequency. You can probably guess by now, if we divide by B minus A equals the height. So the height of our graph is 1 over B minus A, which makes things really, really simple. Let's take a value of x. Let's say x is going to be here. So the probability that x is less than or equal to small x there is just going to be this distance times by the height, because it's a rectangle. Isn't that lovely? None of your funny integration or other weird stuff going on. It's just a rectangle. Isn't that nice? Now, our continuous uniform distribution, the notation for it, we say x, so U for uniform, and then the two things we need to know are A and our B value, because from this you can get the height and everything else. So A and B. So x is distributed uniformly between the values of A and B. Isn't that jolly good fun? So let's have a look at a daring and dangerous example of the continuous uniform distribution. Here we go. So let's say we have a function defined by a quarter and 0 otherwise, so a quarter between 2 and 6. So we're going to sketch a quick graph. Beautiful, look at this piece of art. Between 2 and 6, it takes a value of a quarter, so it's going to look like that, and it's uniform, and down again across. This makes sense because the gap between 6 and 2 is 4, area of 1, therefore our height is a quarter. If we wanted to find the probability that x is less than or equal to 3, well, that's the base of our rectangle here. So there's 3, so that area there. Well, 3 from 2, that's our base, and our height is a quarter. So it's 1 times a quarter, magic! It's a quarter. Isn't that beautiful? What an easy thing to do. it's like, so it's a bit like histograms in a way, I suppose, although that wasn't dealing with the probability, but a similar concept, I guess, where area is the thing we're caring about, and it's nice rectangles. So here's the same graph again. This time, let's go between, I don't know, 2.5 and 4. So here's 2.5, roughly. Here's 4. So this rectangle here is the bit we care about. Well, let's see what our base is. Our base is 4 take 2.5. Our height is 1/4, which gives us 1.5 times 1/4, which is 3/8. Hey, nice and easy, right? Here's the last thing to look at, I suppose. Okay, let's start with defining x as being uniform. And let's say for some reason our data changes or whatever happens to it, and we want to define a new variable. Let's call it y. Now y is when we transform the x values, we're timesing by 5 and taking away 4. Okay, so let's find, so we transformed it, let's find the new values. Okay, so our original one would have been our original graph. Let's see, here's our original graph for x. Went between 3 and 5. Now the gap there is 2, which means our height of that is 1/2. Okay, let's find our new values for y. So it's looking y as well. Well, when x is 3, which is our lower bound there, y is 5 times 3, take 4. Well, 5 times 3 is 15, take 4 is 11. So the lower value of y is going to be 11, which seems to be about there. Not even close. And then our upper value of y was where x is 5. So y is 5 times 5, take 4. 25 take 4 is 21. Upper value of y is 21. And the height of it, well, 21 take 11 is 10. So height is 1/10, which is going to be like down there somewhere. So this is our original function, and here is the one after we've changed it. And y is defined by 11 to 21. Now since this is uniform, and it changes uniformly, we can actually apply the transformation of the mean quite nicely. Okay, so we multiply x, we multiply the mean. If we add on something, we add on something to the mean. So the mean was originally 10, for example. See, that makes no sense, obviously. Okay, let's say the mean was 4, which seems quite likely. You just do 5 times 4, take away 4. That's the new mean. Nice and lovely and simple.